All right, let's solve a mystery. A digital mystery that I guarantee you've run into. The weird case of the disappearing like. You totally know what I'm talking about, right? You're scrolling, you smash that like button, the heart goes red, you feel good. But then you pull to refresh and poof, it's gone. The heart is gray again. You're like, wait, did I even do that? Is my app just broken? Well, the real answer is way weirder and way more interesting than you'd think.
Okay, so how you see this little disappearing act, it really depends on who you ask. If you talk to a junior engineer, they're going to look at that and immediately say, whoa, that's a bug. We got to fix that like right now. But a senior engineer, they see the exact same thing and they'll just nod and say, nope, that's a trade-off. So what is it? Is it a screw up or is it on purpose? To figure that out, we've got to follow the first clue. And that clue, it's not in the code, it's actually in physics. I'm serious, the physics of data. The real reason your like disappears is tied to the one speed limit nobody can break, the speed of light.
You know, way back in the early days of the internet, everything was kind of simple. An app would have one big, single database. You'd post something, and the next person to look would see it. Instantly. No delay. Programmers call this strong consistency. And it was great. It was perfect, actually, until the internet exploded and got, massive. Okay, so fast forward to today. There's no way a single computer can run something like Instagram, right? So they have servers or replicas all over the world. And this is where the magic or the weirdness happens. So check this out. You're in the US. You tap like. Your request zips over to the main server, the primary. That server immediately says, okay, got it, and tells your phone to turn the heart red. Instant satisfaction for you. But, and this is the key part, in the background, that primary server now has to tell all the other servers in, say, Europe and Asia about your like. And if someone in Europe refreshes their feed before that like signal has physically crossed the Atlantic Ocean, well, their server doesn't know about it yet. It shows them the old data, a gray heart. That's our disappearing like, right there in that gap.
And this isn't just some abstract idea. These are real delays. We're talking about the time it takes for light to travel through fiber optic cables. Sending your like from the US to Europe, that takes about 100 to 200 milliseconds. I mean, yeah, that's quicker than you can blink, but it's not instant. It's not zero. And what if there's a network hiccup? Suddenly that delay can jump from milliseconds to minutes, or even hours. This gap is called replication lag, and it's the core idea behind a concept called eventual consistency.
So you're probably thinking, okay, if this lag is so annoying, why on earth would anyone build a system like this on purpose? And that's the million-dollar question. It turns out they have an incredibly good reason. It all comes down to a really tough choice. Really, it boils down to two totally different ways of thinking. On one hand, you have a philosophy called ACID. Now, the letters stand for something complicated, but just think of ACID as the lawyer. It's strict, by the book, and demands that everything is perfect, 100% correct, all the time. Every transaction is legally binding. Then, on the other hand, you have BASE. Think of BASE as the startup founder. It's all about moving fast, being online, and just keeping the lights on. It's okay if things are a tiny bit out of date for a split second, as long as the site is up and running, basically available, eventually consistent. And here's the thing. This isn't just like a style choice. Engineers don't just pick one because they feel like it. They are literally forced to choose by a fundamental law of computer science. It's called the CAP theorem. So the CAP theorem is pretty simple. It says you get 3 guarantees to choose from. Consistency, which means everyone always sees the most up-to-date info. Availability, which means the website is always online. And partition tolerance, which means the whole system doesn't crash just because one network cable gets unplugged somewhere. But here's the catch. You can only have 2 out of the 3. And since network failures happen all the time on the internet, you must pick partition tolerance. So that leaves you with a really tough choice, doesn't it?
And here is that choice, laid bare. Do you choose consistency? Well, that means the second there's a network problem, the site has to go completely offline. Why? To avoid the risk of showing someone old, incorrect data. Or do you choose availability? The site stays up no matter what. The trade-off? Yeah, someone might see that gray heart for a second. Now, if you're Amazon and you lose literally millions of dollars for every minute you're offline, which one are you going to pick? Yeah, you pick availability every single time.
But wait, there's more. Let's talk about pure raw speed. If you forced the system to be perfectly consistent, if your phone had to wait for confirmation from servers in Tokyo and Frankfurt and Sao Paulo before that little heart turned red, the app would be about 30 times slower. 30. That is a huge penalty. It's the difference between an app that feels snappy and instant and one that feels clunky and broken. And we all know what we do with slow apps, right? We delete them. So engineers make the smart choice for user experience. They choose speed.
But making this compromise, choosing speed over perfect consistency, it's not a free lunch. It's a dangerous game. It's like walking a high wire act, and sometimes people fall. So let's look at two real-world stories of what happens when this deliberate trade-off goes horribly wrong.
Okay, first up, GitHub, way back in 2012. We're talking about a replication lag of just a few seconds. Seems like nothing, right? But it was enough to cause a disaster. See, they had an automated script that pushed new code to their servers. And that script, it happened to ask a replica, a slightly out-of-date server, what the latest code was. And because it got old data, it deployed the wrong code to the entire site. GitHub went down. For 2 hours. That's a massive productivity loss for millions of developers. The lesson here was painful, and it was expensive. You simply cannot treat all data equally. For something mission critical, like deploying your entire website's code, you have to talk to the main source, the primary database. No exceptions. All right, our second story is going to sound really familiar, but the stakes were much, much higher. This was Instagram in 2016. People started freaking out because their photos were just vanishing. They'd upload a new pic, the app would pop up a little success message, and then they'd refresh their own profile, and nothing. The photo was gone. Now, the technical reason was exactly the same, replication log. But the human impact was way bigger. Users were furious. They flooded support with complaints. Some even accused Instagram of censoring them. The lesson here was more subtle. It was about psychology. When it comes to your own stuff, the photo you just uploaded, you have an absolute expectation to see it right away. In engineer speak, the system has to guarantee read your rights consistency. It's a sacred trust with the user. Okay, so we've looked at the clues, we've talked about the physics of the speed of light, we've gone over the fundamental laws of computing, and we've seen the battle scars from billion-dollar companies. It's time to close the case. What's the final verdict on the disappearing light? Here's what it all boils down to. Number one, that disappearing light, it's not a bug, it's a feature of a deliberate trade-off made for speed and to keep the site online. Number two, this isn't a choice engineers want to make. It's one they're forced into by the speed of light and that cap theorem. Number three, and this is crucial, some data, like your bank balance or website code, can never be eventually consistent. And finally, number four, getting this trade-off wrong, as we saw, has cost real companies a whole lot of money and trust. So, case closed. The disappearing like isn't a mistake, it's a necessary compromise. But solving this mystery just opens up a bigger, more fascinating one. If this little glitch is built into the very fabric of the internet, how did the absolute best engineering teams at places like Google and Netflix hide it so well? How do they make this compromise feel invisible? Well, that is a whole other story. Thanks for digging into this with me.